Day number 4, you almost made it. Yesterday we talked about modular symbols and modular forms. How do those two things relate? They're dual. So modular forms are functions on the upper half plane, blah, blah. Okay, I don't know. So what we do is we make this abstractly defined Q vector space, have a group act on a bunch of rational numbers, something you can represent in exact arithmetic, actually do your computations by hand. We discovered at the end yesterday morning, that gamma 0 of 11, x naught of 11 has genus 1. Okay, so today what I want to introduce is the action of Hecke on this module, which allows us to compute the Q expansion. So it gives us more data than just the dimension of a vector space. So these vector spaces have naturally equipped commuting operators on them, and that information is enough for us to deduce the facts about the modular forms that we would like to integrate and play with otherwise. Okay? So here's how the Hecke operators are defined. So for a positive integer n, we define a set of matrices, which are the set of matrices of determinant n up to left multiplication by a invertible matrix. So I'm going to call this fatty theta of n, and explicitly these are the matrices A, B, 0, D in M2Z with A greater or equal to 1 for normalization purposes, A, D equals n, that's the determinant, and 0 less than or equal to B less than. So that's the set of matrices. I claim that this is the same thing as if you took GL2Z representatives of the set of all 2 by 2 matrices with determinant n. Okay, so this is like a partial Smith normal form where you're allowed operations on the left. If you can do them on the right, then you have an actual Smith normal form, and you can put it in diagonal form. That's what you do when you prove the fundamental theorem of finally generated abelian groups. These would be the invariant factors, the A and the D. And if you restrict yourself only to left actions, then you can't quite cope with the thing in the upper right-hand corner. That's how you prove this equivalence. Okay, so explicitly, the most interesting case is where n equals p is prime, and then your theta p, how many elements are in the set? Well, let's see, we have to take 2 positive integers that multiply to p, not too many choices for that. I can either take a equals 1 and d is equal to p, or a equals p and d is equal to 1. If I choose the d is equal to 1, that doesn't leave me many choices for the b, but if I take the d equals p, then I have a good number of choices. Okay, so you see that this set is exactly the special guy here, and then I have a whole bunch of other choices. Did you see that? Still awake this morning with me? Okay, so the number, stop me if I say something that's not clear. Okay, so another way to think about this set theta n is it's naturally in bijection with lattices of index n, set of lattices. And the bijection is you take such a matrix A that belongs to your set, and you make the associated lattice where you've written out a basis of a choice of basis for that lattice as the rows of that matrix. Okay? So that would mean that you take the z-span of A E1 plus B E2. The E1 and the E2 are the standard basis elements of Z2. Okay, you could write that as A comma B if you wanted to. Okay, so z squared, I think that's clear. So this thing is bijective. So the set is really representing the sublattices of, so I'll leave that as an exercise for you to check that, but I think I've said enough that you can prove that yourself. How would you write down a sublattice? Well, you'd have to choose a basis. It's determined it's going to have to be equal to the index, etc. Okay, then you have to choose based on rows or columns whether you're acting on the left or right. And as long as you keep that sorted, you believe this. Okay, so really what we're doing when we have a set theta n is that we're summing over sublattices. And you guys know the interpretation of modular forms as being functions on lattices, homothetic classes of lattices with certain scaling factors. So this is going to be like averaging over sublattices of a given index, which is a very natural group theoretic thing to do. There's other interpretations of the Heck operators that come from double cosets or all sorts of ways of life, but this is the most concrete for classical modular forms. And anyway, you don't have to think about that if you don't want to. Just you have a set of matrices, okay? So now let gamma be a congruent subgroup. So congruent subgroups, remember, have a level n. That's the smallest positive integer such that gamma of n is contained inside the group gamma. So here's how we define Heck operators for modular forms on gamma. So I can only do it, well, it's enough to do today for the case where the GCD of the little n for the Heck operators and the capital N is equal to 1. For when this condition is not satisfied, we have a different notion of Heck operator. It still looks like averaging, and the operators tell you important facts about your modular forms. But for today, we'll be able to see quite a lot about our modular forms just from this subset. If you're thinking about the primes, n equals a prime, you only lose out on finitely many primes by this condition, right? Those dividing below. Okay. So we define Tn. So Tn is a map from, this is not a scripty S, this is the regular S space of modular forms. The overloading of the regular S and the scripty S is because they're kind of the same thing, you know what I mean? They're not literally, one is twice the dimension, that kind of thing, but if you, in any situation where you have to make something scripty or unscripty, it's probably a theorem or somehow related to telling you something about the mathematical world. So this is regular Roman S, your regular modular forms with happy Q expansions and so on. Okay, so this is a Heck operator. Definition of the Heck operator. And what does it do? Well, it's going to have to take a modular form. We've thought of these as invariant differentials on the modular curve. This is a vector space, C vector space of dimension G, where G is the genus, and that's the definition of genus. So I take one of these complex holomorphic functions that vanish at infinity, and I make for you a new function, Tn of f. Okay, so I'm off to a good start. Should probably tell you what the Tn of f is. Okay, so this is a map from the upper half plane to C. Okay, and it's defined by Tn of f. Well, it's a function, so when I plug in C, everyone can still see that on the side. I'll try not to cram in too much on the bottom here. All I'm going to do is I'm going to plug in all of the, I'm going to slash with all of those matrices there. Okay, so to avoid writing down slash operator, which is just a reshuffling, I take all my theta, sorry, I'm going to call them delta in my theta n, and I plug in f of az plus b over d. Right, that's how you would usually slash with an element there. I'm going to take a weighted average here, and I'm going to weight it by d to the minus 2. That's a scaling factor which has explanations in terms of automorphy and so on, but just think about it as being a weighted average instead of literally an average. Okay, that's the right thing to do. That's the definition of the Heck operator. All right, so what, if any, properties do Heck operators have? Well, because they're averaging, they should somehow, I mean, if I'm going to hit things with gamma, I'm going to preserve this set of lattices of index n. So we should expect nice properties whenever you're averaging. Okay, so maybe some easier ones to start out with is if you take a Tn and a Tm, then these things commute whenever the GCD of m and n is equal to 1, and I'll have the prevailing hypothesis that I've only defined the Heck operators for things relatively prime to n. So implicitly there, the m and the n are relatively prime to the capital N. Okay, so why is such a statement like this true? Well, you have to decide about what happens when you take sublattices of index m and sublattices of index n, and how you might relate those two. And the answer is the Chinese remainder Sun Tzu theorem. Okay, so you want to combine, I don't know, just think about the quotients of the z-squared mod the two lattices. One's going to be some abelian group of order m, one's going to be an abelian group of order n. Well, those two things play nicely when m and n are relatively prime. Okay, so that's, the m and the n don't see each other. You might ask in a more refined way, what happens if I take, well, this reduces to the prime case, so then you might want to know the prime power case. You might want to know how does the higher prime power relate to lower prime powers, so you have to work that out. If you've never seen this before, a really nice place to read about it, which is self-contained, very concise, is Sarah's book, A Course in Arithmetic. Okay, so when you have a bunch of commuting operators on a space, well, if you have, if these operators were diagonalizable, then you have a common eigenbasis, and it's even true that these are self-adjoint with respect to a natural inner product. The Peterson inner product is obtained by integrating, and its definition will not. Well, if you guys want to see the definition of the inner product, I can write it down, I guess. So if you have an f and a g, you want to integrate f and g on gamma. Some people like to keep their gamma around. The definition here, all you do is you integrate over a fundamental region. When this integral exists, and you do f of z, g of z bar. You need a factor here to make the integral well-defined in terms of coordinates, and then you do this with respect to the hyperbolic theory. Okay, so if I was integrating the function 1 over with respect to dA, that would be the area of a fundamental domain. You guys know what fundamental domains look like. You can count the number of triangles, and you know how much area is in an individual triangle, but here I'm averaging the functions with respect to, well, and because you want it to be self-adjoint and these are complex values, you put the bar in as usual to get something which is positive definite. And okay, so these are properties that we will use. So if your function f of z, you write it in a Fourier expansion, it starts out an q to the n with n's equal to 1 because it's a cusp form. So in particular, it vanishes at infinity. All my guys are cusp forms. There are issues with this integral if you try to integrate two Eisenstein series, one with the other. The integral you have to regularize, but as long as you're dealing with cusp forms, there are no problems there. So then you can see explicitly what the Tp of f and similarly the Tn of f, if you want to write it all out, what it does to a Q expansion. You could also take this to be the definition of the Heck operator if you wanted to. It sort of takes the, why am I writing it as an M? Oh, I guess I want to be careful about N's and M's here. So you sort of take a weighted combination of the coefficients. You can sort of see that that's a natural thing, because these things, when they act on infinity, you're going to introduce various roots of unity. And does that make sense? Like when you plug in c, the denominator of d is either going to be p, which means you're interested in 2 pi I over p, and those roots of unity cancel in a nice way to give you a function like this. Okay? Is that all right? I'm just throwing definitions at you until you complain, but you guys aren't complaining, so I'm going to keep doing it. Right? The definitions are almost over. The most important one, and maybe the fundamental one, is that if you now, with respect to these two properties, if you're self-adjoint with respect to these inner products, and these guys all commute, well, and Tp commutes with itself, and according to this, so then you have a common eigenbasis. So if you have an eigenform, so an eigenform means Tn eigenform with, so you can normalize it so that A1 is equal to 1. Then your Tn of f is An of f, for all n, still with this condition, GCD n equals 1. Okay, so that follows from the formula that we just wrote down. I think you could actually, what I've given you is enough to verify a lot of these properties yourself. Okay. What happens here if A1 is equal to 0? Well, it turns out you can't be an eigenform unless you're 0 by this property. Okay, so you could relax this condition. You would still have this, but you have to put an A1 out in front here. You conclude that your thing was 0. What other questions do you guys have about this? Yes?
The definition of
This thing here.
What if P does not divide N?
You call it 0. Thank you. That's a great question. Anything else? Okay, so that's all well and good, but the whole point of that 7 minutes, okay, a little bit longer than that, was we don't really have any control over this world. I mean, we do in our heads, but not really in bits in computers, because it's hard to write down complex numbers and so on. So we're going to encode modular forms by the Q expansion principle, by its Fourier expansion, by these ANs. So if we could just get our hands on these ANs, we'd be good. The ANs are the eigenvalues of Heck operators. So, as we heard this morning, modular forms, cusp forms, are dual to modular symbols, cuspal modular symbols. So if we can transport the action of Hecke to our modular symbols, then we just have to like mess with alphas and betas, 1/3 and 1/2, have those matrices act, and then we'll get Heck operators out, and we can diagonalize them and go to town. Okay, that's the basic. That's what's happening in Sage and Magma, and the first, even the earliest versions of where modularity was being checked. It was done using exactly this relationship. Because you have strong control over the homologies, you might as well. Okay, so let's have it act on modular symbols. You guys ready? So what does a modular symbol look like? Well, I can take my alpha beta in some, now I have to make it scripty. So let's see, you guys tell me, how should I define the Heck operator? My group hasn't changed, same group, nothing's there. I'm still going to define them only for co-prime. How should I define this Tn alpha beta? Aren't that many choices, right? Still have my theta n, my fatty theta, right? There's a bunch of matrices. Yeah, let's just jam it in there. Okay, so sum. Why not? And then have the delta act. This is one example of how sort of when you work sufficiently abstractly in mathematics and just the right level of generality, you're not distracted by all of the possible moves that you could make. You just have the thing that's in front of you, and if you act naturally, then you find beautiful theorems. So this is why. You guys see what I'm saying? There's really only one natural choice here. Okay, so maybe we should recall integration, because that's the relationship between modular forms and modular symbols. So if I take my Roman S2 of gamma and my scripty S2, that's not a zeta, just getting excited, I can integrate one with respect to the other and get a complex number. So I take my form F, and strictly speaking, I have to take a linear combination of modular symbols such that it gives me a linear combination of paths in X of gamma. So I'm just going to define this on the M2s extended by linearity, right? If I had such a guy, I would write it as a linear combination of the alpha beta. Is that clear what I'm monkeying around? Okay, so you can't literally, just like when you find something on a tensor product, you have to show sense later. Anyway, so what do? You just integrate this sucker. You stick at a 2 pi I. I explain where that comes from because of the change of coordinates from Q, e to the I, 2 pi, when you change the coordinates from Z to Q. Okay, I feel like writing this down too, I don't know why. I guess you wanted to think about integrating a Q expansion, which if you have a Q expansion, that's a power series thing, you can integrate it by term. The integral is going to be Q to the n plus 1 an over n plus 1, just like you do in calculus. Okay, so that's why you see the 2 pi I wants to go away, because you have integer coefficients. Now you still have integer coefficients. And then what do? Well, I guess you plug it in a half and a third, right? Or whatever you're... Do that? Okay, so what do you know about this pairing? Well, I guess it's the theorem last time was that it was perfect after you appropriately consider the over R or something like that, so to make sure that you're working over the right space. You can interpret this, I guess we had Q vector spaces, so there's a way to interpret that just fine. This is a complex vector space. This is a Q vector space, so you have to worry about over what field you're working, but I hope I made that clear yesterday. So now, the nicest possible thing is that the integration pairing is compatible with the heck operators, right? Those are the magic words that you want to hear me say. May all your diagrams commute, and may all your operators be compatible. It's the blessing that we did. So what would it mean to be compatible with heck operators? So that means this is the usual self-adjoinous property. So if I do my Tn here with an alpha beta, it should go on the other side, right? Okay. Now you think about this for just a second about what that's saying. Can you prove that? I think you can. This is a level of an exercise. It's called you sum and you change variables. Right? I'm plugging into the f sum, it's erased here now, but az plus b over d. If I want to undo that change of variables, then I have to make a substitution. Z goes to az plus b, which is exactly the set of elements delta, and that means I have to change the limits of integration. And the alpha beta are exactly the elements in the limits of integration. Okay, so if you write this down, it is a very short proof. It's almost a tautology after it's, okay, but you have to write it. Okay, so sum and change variables. All right, so given a modular symbol for gamma, we need to write it in terms of a chosen basis and use a reduction algorithm. So now something, but before we get going on that, I want to show you how to actually physically compute with this, but this is the end of the definitions portions of the morning. Do you guys feel, is everything clear what's happening? So I transported the action of the heck operators from classical analytic definition to modular symbols definition, and by this compatibility, we'll see an isomorphism of Hecke modules, which is to say that if I compute an AN on an F on one side, that corresponds to an AN on the other side. I saw a pre-question, yes?
As to what are actual samples?
Just wait two.
No, what about algorithms?
That's a great question. I hope I'll have some time for some comments on that later.
Oh,
Yeah, we care about higher weight two, but weight two is already a good place to start. You have to stick in a coefficient module. 2 is for the weight of the force. Okay, ready to see how this works? So if we wanted to compute this in practice, remember we did this at the end. We had a basis for S2 of gamma 0 of 11, and it was given by the modular symbols. What were they called? 0, 1/3, and 1/3, 1/2? I mean, ta-da, you have your modular symbol, okay? What the heck do you do to that? Okay, well you can compute these matrices, right? I told you what they were. Pick your prime key, which is not 11, 2. Write down the 3 matrices we wrote down there, right? 2, 0, 0, 1, right? Those 3 matrices. Plug them in. Okay, now you have a new modular symbol. What are you going to do with that? Okay. So is it clear what our next task is to write that symbol in terms of our basis of modular symbols. So in other words, we had something in a finite dimensional vector space which is a quotient of 2 infinite dimensional vector spaces. So I need to be able to take a representative in the bigger thing and rewrite it in terms of my fixed basis. Okay? So again, you'll see a reduction algorithm. I've given you a way to do this using theory symbols. So if you want to think about it that way, you have to take each one of these guys, which will be some new fractions, and rewrite those fractions and then symbols as a linear combination. So you trail your path all the way back to the fundamental domain, and that gives you a general way of writing down just use it purely in terms of the theory symbols. Okay, so need reduction to make this computable. No one does this, but it's possible to do it. So need reduction theory can use theory symbols and the reduction theory that comes from them. This is not what is usually done, okay, because there is another way which encodes basically the same information, but it's more optimized. Okay, so when you see Sage or Magma making choices about things, it's because they've implemented something which is not theory symbols as modular symbols, but instead something called Manin symbols. And with Manin symbols, you're basically working with cosets instead, and you rely directly on the Euclidean algorithm like we saw in the second lecture, to write them down. So that gives you a way to sort of transport the reduction theory on SL2Z directly to your group gamma by having it act by permutations on the cosets. So that's a very natural alternative. But there are other situations where you don't want to have to do that. It only really works for gamma 0, gamma 1, and maybe there's other weird groups. So I don't know, this would be an interesting computational project if you wanted to get to know fairy symbols and modular forms better. You could think about how this works even on our gamma 0 to 11 keys. But for now, I want to spend 15 minutes telling you about what are called Manin symbols. So first, I want to make a generalization of the, in PSL2Z, the modular symbols were a cyclic module over the group algebra generated by the single symbol infinity 0. Let's remember that theorem, that's called the Euclidean algorithm. So here we get the same thing if we take cosets. Okay, so if you take PSL2Z and you write it as a bunch of whatever side cosets these are. I guess these are left cosets, right? They're right cosets, left. Okay, so if you write it as a gamma is a finite index, so there will be exactly as many of these cosets as the index of the group. Okay, so if you write it like this, then what's the generalization? Then the answer is that gamma I, infinity 0, generates M2 gamma. So the proof is the same. You might also think about how you would capture this proposition without reproving it using the Euclidean algorithm, but instead just using that proof for SL2Z. See that there's a natural action via permutation of the cosets. Maybe you don't have to do that, you just repeat the same. So what does that mean, for example, for gamma equals gamma 0 of P prime? Well, they're really going at it out there. So there is a set of left coset representatives which looks very similar to the representatives I wrote down for theta. Because of left versus right issues, they aren't literally the same, but they're pretty close. Okay, so there are P plus 1 matrices that I've written down there. One of them is the identity coset. I've got these translates here. You see the P of them, so 0 up to P minus 1. And here's your guy S, which does not belong to gamma 0 P because the lower left entry is not divisible by P. Okay? So you should think, there are lots of ways to think about why these are coset representatives. It has to do with the natural action on P1 of FP. You want to think about it that way? I think because my time is limited, I just have to tell you facts like this, and then we get to practice with them. But each one of them has a little story to tell. You want to get used to it. All right, I'll tell you one thing. I can't help myself. If you take gamma 0n mod PSL2Z, so n is now does not have to be prime. There is a bijection between the cosets here, the left cosets, and the set P1 of Z mod NZ, and it just sends a representative A, B, C, D to the element C colon D as an element of the P1 of Z mod NZ. What's P1 of a ring? Well, I get to choose two elements from the ring. They need to generate the unit ideal of that ring, and I consider them up to scalar equivalence by units in the ring R. So here P1 Z mod NZ is the set of pairs C comma D from Z mod NZ squared, such that the GCD, common GCD of C, D, and N is equal to 1. So I don't want to have a prime that divides N, that divides both of the C and D, and then I consider them up to scalar multiplication by Z mod NZ star. So So this is the action where I take CD and I declare that it's linearly equivalent to lambda C, lambda D for lambda in Z mod NZ star. Just specializing the definition of P1 of a ring to Z mod NZ. So just think about what this tells you for n is equal to prime. So what is P1 of FP, right? So Z mod PZ is FP. What's P1 of a field? Well, it's the set of elements in the field together with the symbol infinity. And if you write it as, you know, the one coordinate being 1, then you list all your elements of FP, and then you have the other guy, which is called 1, 0. If by the Chinese remainder Sun Tzu theorem, if you have Z mod NZ being a product of such local rings, Z mod P to EZ, you have to sort of you have to Chinese remainder them together, and you don't have to worry about the powers of P, so it's encoded inside this guy. The map is just helping you to keep track of the fact that you're acting on the left, and your lower left entry is divisible by n. So you might practice with this by taking a matrix here, multiplying it by x, y, n times z, w, and seeing that this class CD is well defined. Okay, to prove that it's bijection is not much harder than that. All right. So that tells you this. Do you see what we're doing right now? We're like specializing a general algorithm to something we'd be super concrete about, so we can have efficient algorithms, okay, and make it easier even on you as a human to think through it. So here, cosets are like P1 of FP. So we're going to keep, we'll call these guys something. We'll give them names, and that'll give us a way of working with modular symbols instead of theory symbols by elements of that P1 of Z mod N. Okay. So what does gamma 0 of 11 look like? So my S2 of gamma. So if I put these two things together, so first of all, if I write them as left cosets, all I have to do is hit the matrix with these guys. I have written down a nice set of representatives here. So what does that say for gamma 0 of 11? Well, first of all, I have to hit infinity 0 with the identity matrix. All right, that's the easy one. What comes next? You guys help me? Are you still awake? What do you do if you hit this matrix and you LFT this guy? What do you get? This is the one that says Z goes to Z over Z plus 1. So as I plug in infinity by taking limits, I will get 1, the leading coefficient there, and 0 goes to 0. Okay, are you ready to conjecture what happens more generally for the rest of these? Okay, well I'll tell you, it's a 1/10. You go all the way up to 1 over P minus 1. I think that's clear now. When you plug in the infinity, you get 1 over A. And this other guy is swap map. It's interchanging 0 and infinity, right? So this becomes 0 infinity. So by the usual property of modular symbols, this is the same thing as minus this. Okay, let's give these suckers names. Do you see good names for them? I'm going to call them just by the corresponding label in the P1 of FP. So I'll call this guy, this symbol 0, this symbol 1, all the way up to this symbol is called 10, and this symbol is called infinity. Okay, so this is in the natural dictionary with the elements of P1 of F11.